Yeah? Okay. Hello, good morning. My name is Sergio Rivera. I'm the CTO of the company Nanoker Research. And I will give a talk with the title Special Ceramics for Top-End Industrial Applications and Harsh Environments. So in the talk, I will present a little bit the company in one slide, and then I will go through different technical ceramic materials and products, giving examples of parts that we produce in the company. So Nanoker is a company manufacturer of technical ceramic parts. It was created 11 years ago. We are based in Asturias, in North Spain. And we are a company that we define ourselves as ceramists. So we start from powder, and we produce finished parts, trying to cover the whole process. We are 25 people producing standard ceramics, but also trying to develop new materials, producing parts based on that materials. We are in a growth phase, so we hope to reach 5 million euros revenue in 2026. And we have a manufacturing in Spain of 2 buildings with 2,500 square meters. And we are selling in Scandinavia since around 10 years ago through our representative here, which is a company, KG Fridman. So basically, I will speak a little bit about different families of technical ceramic materials, and then I will give some examples of these parts produced by these families. So basically, you can classify of different ways technical ceramics, but one of the most typical ones is the classification about according to the chemical nature. So you can find oxides, mainly zirconium oxide or aluminium oxide, which are used in structural applications and also biomedical applications. You can find as well carbides, like boron carbide, silicon carbide, titanium carbide, and now it's widely used, these materials. Now they have a lot of attraction because of they are using ballistic application, for example, because they are hard and light. And also another family of materials is called nitrides, mainly silicon nitride, boron nitride, aluminium nitride is most typical materials in different applications. And also probably with these three oxides, carbides, and nitrides, you cover probably around 90% of the technical ceramic components around the markets. But also in the last times, receiving a lot of attraction, some materials called borides that are used now a lot in the space industry because of they resist very, very high temperatures without erosion and corrosion. So I will go through some of these materials, mainly the three main oxides, carbides, and nitrides, giving some examples of them. So the first one, aluminium oxide, is probably one of the most common materials in technical ceramics. It's a material coming from a natural resource, which is a bauxite, which is a rock that is mined. And it has, apart from alumina and oxygen, it has also other content in iron, for example. Through a process called Bayer, you can purify the raw material and obtain alumina of 99.7% of purity. The trace elements that you have in alumina, like silica, iron oxides, magnesia, sodium oxide, are coming from this process, and they determine some of the material properties of the ceramics as well. You can reach higher purity if you want, but it's not coming from this process, and you have to synthesize the material, which is much more expensive. Only for some very specific applications, for example, in semiconductors, where alumina is used as a wafer carrier, you need more purity than 99.7. But for most of the applications, 99.7 is enough for aluminum parts. If we have to produce parts based on these ceramics, we need to condition the powder. So depending on how we process the ceramic, can we produce by pressing or by slip casting, we need to condition the powder depending on the final product. The general properties of aluminum oxide is a material that has high temperature resistance, 1600, high resistance to abrasive wear, good electrical insulation, is a market standard for electrical insulation applications, and also it has a very good chemical resistance against different let's say, acids and alkalis. Some examples of parts that we produce at Nanoker in this material. For example, laboratory wear equipment. We produce this kind of crucibles and trays that are used for companies producing, for example, powder, and they need to make some kind of treatment to the powder, and they need a container to keep a high temperature and not react with the material. So they use this kind of parts. And also we produce by casting milling jars, the one of the right. It's mainly used for mixing, blending different things, pigments, also powders, and they need a container with a high purity, not, let's say, reacting with the material that they are mixing. So these are some examples of parts that we produce by casting. And then for products produced for other application structural, the two pictures of the stream are not from Nanoker, are from other companies. But this alumina is mainly also used for, let's say, feed fruits. It's used as electrical insulation. It's used in big science, like the part in the right. In the big science industry, there are in particle accelerators. They use alumina ceramics for isolating the magnets. And also, there are some parts that we produce in Nanoker for different applications, for wears, valves, pistons, and also substrates for thermal dissipation. Another material of the oxides are the zirconia. Zirconia is an important material that is also coming from a natural source, which is zircon, silicate. There is a purification process to obtain zirconia, and to reach a structural material, you need to add stabilizers, mainly rare earth oxides, like yttrium oxide, cerium oxide, or magnesia as well, are critical for this stabilization process, and they also determine the pricing of the material, because these rare earth oxides are now submitted to a strict, let's say, 80% of these materials are in China. Depending on the stabilizer of the zirconia, you have different properties. If you stabilize what is called tetragonal zirconia, you have very good mechanical properties. If you stabilize the partial stabilized zirconia, you have good properties against high temperatures and thermal shock. And if you fully stabilize the zirconia, you have, for example, oxygen conductivity that is used, for example, in oxygen sensors and some of the applications where you need to measure the oxygen content of the atmosphere. The properties of the tetragonal zirconia is high strength material, 1200 megapascals, high toughness, sometimes it's called ceramic steel. It's not a plastic material like metals, but still it resists some kind of shocks. But of course, it's a brittle material compared with metals. It's biocompatible. It's one of the materials used for substitution of bone in the body. And as I explained before, you have, if you fully stabilize the material, you have oxygen conductivity. Some examples: tetragonal zirconia, which you reach that if you add, for example, 5% weight of yttrium oxide. You have this combination of mechanical properties of strength and toughness, which are quite good. And here below some examples of Nanoker examples of the extremes. This is a dental implant that we will get the CE mark in the next months. It's not pure zirconia, it has some alumina as well, but it's now the ceramic standard for the dental implantology is zirconia. In the center, it's not pure zirconia as well. It's doped with alumina, but it's the hip prosthesis now that are produced by mainly by Cerantec company in Germany. It's now the market standard for ceramic hip prosthesis, and they are made of zirconia and alumina. It's a mixture of them. Then in the right, you find a part that we produce in Nanoker. It's a very, very small part, but we produce that for a medical device manufacturer, and it's for killing tumor cells by microwave ablation. And it's performed in zirconia because of his biocompatibility and also because of compatibility with medical imaging. The downside of this material is that it doesn't resist thermal shocks. So you cannot use the tetragonal zirconia for applications where you have to have a high thermal gradient. But for these applications, you can use another grade of zirconia. Changing the stabilizer, you can partially stabilized zirconia. It's called partial stabilized zirconia. And you have tetragonal and cubic phases. And then you lose some of the strength of the material because of this mixture of phases. But at the same time, you gain, let's say, a high, let's say, thermal shock resistance. This material is used, for example, in contact with copper for extruding copper and copper alloys. This is an example of a bar, and this bar goes through the ceramic, which is shrink-fitted in a metallic case in order to resist the mechanical forces during the extrusion. Other examples of parts, also for the same application, for copper and copper alloy extrusion, that can be produced in magnesia-stabilized zirconia, which is this material referenced here. So this is oxidic ceramics, aluminium oxide, zirconium oxide. Moving now to nitride ceramics. There are different materials in this family, but silicon nitride is one of the most well-known. It's material known as all-rounder because it's valid for a lot of things. It has very good mechanical properties, but at the same time, it also has good thermal shock resistance, not as the same as the yttrium-stabilized zirconia, for example. And it's widely used in contact with molten metal because it resists the thermal shock and it's not wetted by molten metal, so it's mainly used in foundries. And also, pure silicon nitride, or what is called sialones, which is a derivative of silicon nitride. This is silicon nitride, but adding some additives to decrease the sintering temperature and reduce the cost of the material. Cutting tools, you see bottom right, are one of the parts that are produced with sialones of silicon nitride, and they are used for machining nickel-based alloys and also hardening steel. Before going with the next materials, I would like to explain a little bit one of the technologies that we have in Nanoker for producing ceramics. As you know, the ceramics you need a heating process, sintering process to get the full densification of the material. It's normally done in batch furnaces with resistance heating indirectly the material. In this case, in the spark plasma, what we have is a technology which is a pressure-assisted sintering technology. You have a mold of graphite, you fill the mold with powder, the powder of the material that you want to get dense, and you apply pressure, and at the same time, you pass electric current through the mold and material system, so the material behaves as a resistant and gets heated by Joule effect. So what you have is a direct heating in the material, and you can sinter the material very fast, much faster than if it's done in a normal, let's say, sintering furnace. And with the pressure application, you get completely full densification. The downside of this technology is that you can only obtain single shapes, like plates, because it's a uniaxial press. It's very difficult to obtain custom-made parts. You need to machine afterwards, and the material is hard. But we have this technology to obtain plates up to 400 millimeters of diameter, and size depending on the material, the thickness from 3 millimeters to 40, 50, 60. And this technology is being also industrialized. This is a mold inside the machine. You can sinter the material only inside the mold, but if you put a preheating channel and a cooling channel, you just preheat, then you make the pressure and final heat in just 10, 15 minutes needed, and then you cool down. So you can produce one part every 10 or 15 minutes in a ceramics, which is really very, very, let's say, impressive. So with this technology, we produce more materials of the families that I described before. Boron nitride, it's a material known as white graphite, is very soft and easily machinable, but it resists extremely high thermal shock resistance under different environments, and it's not wetted by molten metal as well. And we produce this material by SPS, and we do a composite. We don't do a single boron nitride because it's a very soft material, and in contact with molten metal, it's not wetted, but it's eroded. So, but if you add zirconia, for example, that is what we do a composite of boron nitride and zirconia, you don't lose part of these properties of the boron nitride, so the thermal shock resistance and not wettability, but you add some hardness. So you can have a good compromise without losing the properties. This material is used in horizontal casting of stainless steel as a part called brake ring, which is the one that you see here. And it's used in the atomizing of metal powders, which is now widely used for obtaining powders for 3D printing, for example. They melt the powder, the material, and they pass through an atomizer, and they molten the metal, and the metal goes through the nozzle, which is made in this composite. And the metal does not clog the nozzle because it goes through the nozzle, and it resists the contact with the molten metal. So it's an interesting application for this kind of materials. The last two slides, aluminium nitride is also one of the materials now receiving attention because it's a very, very good electrical insulation material, but at the same time it's a very good thermal conductor, which is not easy to find. Normally these are opposite properties. So you can find these properties of thermal conductivity, 200 watts per meter Kelvin, which is quite high for a ceramic, and very good electrical insulation. And of course, resistant to high temperature, more than 1,000 degrees. And the same strategy, if you produce a composite, if you add, for example, some boron nitride, the material is very hard, but if you add some boron nitride, you can machine the material with tungsten carbide tools, with conventional tooling, without using diamond and grinding processes, which makes the parts less expensive. And it's a material widely used for heat dissipation and also in contact with power, for dissipated in power electronics, because it has a thermal expansion coefficient very similar to silicon, which is 5. So it doesn't generate stresses due to mismatch. So some examples of parts that we are producing here for CERN in Geneva, they use aluminium nitride for dissipating the heat in some of the detectors. And then the last slide, silicon carbide is a family of materials that are also very important. It's a material with, you can produce it different ways, but it's a material with high resistance to corrosion. It's very difficult to get full densification in pure silicon carbide. So you need or pressure, or you need to add some additives. In some strategies, they add infiltrate silicon, and it's what it's called CSIC, when they infiltrate silicon in silicon carbide matrix. But the limitation of this material is 1300. Silicon carbide pure, you can go higher in temperature. And other grades are also produced, like liquid phase sintering, but it's a material very interesting because it has a lot of resistance to chemical attack. It's used in pumps a lot. It's very hard material, just below boron carbide. It's one of the hardest ceramics, and it's a low dense material. That's why it's used in ballistic protection and armor protection. And this is a plate obtained through the spark plasma sintering process. It's like, I think it's 230 millimeter in size. And these are some examples of a ballistic plate also produced in Nanoker, and another part for aerospace. Well, that's everything. Thanks for your attention.